Well, it's been a few days, maybe about a week since I shot that intro, or the first half of this video, where I was scanning the suspension and, collecting the data. And when I started this video, I was talking about McPherson strut. That was the idea was, let's explore this McPherson strut idea. Let's figure out what to do with the suspension. Let's nail this thing down, because I've gone around and around on suspension ideas since I started this project. First it was, oh, well, what can I do with this stock suspension? And then it was like, could I use a different knuckle and like change the geometry and, really get it dialed in? And then it was like, well, maybe we could do something simpler, maybe McPherson strut. And so eventually I realized I need to get better data, because I had just, basic measuring tape measurements, and I just wasn't that confident in them. Well, after having a lot of playing around in the software, this is what I've come up with. So let's go in the office. Okay, so we're here in the office. I've got my computer here in Blender. This is my 3D software of choice. It's not really a CAD software, but it's what I'm good at, so I'm using it. And here is my finished scan. So first off, we'll start with just what I scanned on camera, what you saw there. So this is what I got from that scan. I got the lower control arm here. You can see that we'll do this. See, I've got this, you can see the lower control arm clearly, the track rod, its pivot point, and if you come around here, you can see the CB flange. You can even see the inner pivot point there, and of course you can see the bump stop right there. The this area here, the control or the spring pocket, all this came out very well. And you can even see detail up in here, so I'm even able to check tire clearance. But also what worked out well is I've got quite a bit of the fender skin here, so that I can see how my tire is going to interact with the fender lip and all that. So I did a little extra scanning. I grabbed a little more detail of the tie rod area, because I didn't have this previously. I didn't get that quite in the initial scan, so I just kind of aligned it up where it goes, and that way I can confirm my steering geometry. In addition to that, I have the standard control arm, or the upper control arm here, that I had scanned before. This scan turned out really nice. You can see how clean that is. I mean, if you wanted to use this for a render or something, it's almost ready to go. So that was that there. This is just the raw scans. You can see here I've added some circles and just tried to align them to the points in the control arm, so I can approximate pivot points and all that. Let's actually go back to this, because I forgot to show you something important here, which is this. This. Boom! You can see right here, I've got full photo textures of the object. So when I look in here, you can see the marks I made on the frame rail there. My points. And so that's what I was able to scale this whole model off of. And of course, I just simply aligned this frame rail up vertically. So I did that there. So, and if you see the upper control arm too, see I've got marks I made on this. I did actually a little more preparation work on this. I got my 2 marks here, my measurement, but I also backed all of the bolt holes so that they would scan well, and that really did help. They scanned very well. So then, let's see what I came up with. First up, we've got this here. Now this is This here is a simplified drawing of what I could do with a McPherson strut style suspension. So I've modeled a wheel, a very rough wheel and tire here. This is a 265 wide or 265 section width tire, and the reason I put that in there is that I want to put a lot of tire on the front of this car. I want it to be a proper, good handling car. So that's my tire. It's 25 inch tall, 265, and then I've modeled a 15.5 inch inner diameter. So what I'm trying to approximate there is the inside diameter of a 16 inch wheel, because I want to be able to go down to 16s for like a rally setup, and then probably have like a 17 or 18 for the tarmac setup. And so the problem with this system here is that these lines here indicate the control arm angle and kingpin inclination angle. Now, grab this guy here. As far as KPI is concerned, I'm at about 12 to 13-ish degrees. From what I've seen online, that's pretty normal for a McPherson strut car. So ultimately, I think with this setup here, I'm not that far off. I think it's pretty much what you would find on a McPherson strut vehicle. However, this is where it's not so fun, where it wants to sit stock. The steering axis here gives about a 3-inch scrub radius on this wheel and tire. And with this wheel and tire, even here, we're sitting at, what is that? That's about, 0.69 inch. So that's like, probably plus 20 or plus 15. It's a really low offset wheel. And if you wanted to run a higher offset wheel, to get it close to that steering axis, you're probably going to run into tire clearances for one, and for two, the track width is going to be super narrow. Well, I should say either the track width is going to be super narrow or the kingpin inclination is going to be really extreme, which is not a good thing for a McPherson strut or for any car, because there's two major downsides to a McPherson strut. Number one is that it's hard to get a lot of camber gain in bump in a McPherson strut geometry. The other thing, and this is something that I learned just by going through this process, researching it, is that when you have a high kingpin inclination angle, you actually get camber loss as the wheel turns. That's counteracted by some degree by your caster angle, which gives you camber gain when you turn the wheel. But it's still a compromise. And so the downsides really started to add up. Poor KPI. A poor caster gain, camber gain. And ultimately what it ends up with is probably going to have a bad steering feel. It's probably going to have a bad contact patch. And ultimately I decided this is maybe not the best way to go. And so what I scanned next is this. This is a steering knuckle from a Chevy S10. This particular one I think was from an 88, but the geometry-wise are all the same from 83 to 02 or whatever the last one they made was. The only thing that changed was the brake hardware. But anyways, I'm getting into the weeds already. So I scanned this. I used the same process to scale it. And this was actually my original plan for the car, was to use an S10 knuckle, because I know that the hub assembly bolts on with the same pattern, and I can bolt the Eagle knuckle into this, Eagle hub into this knuckle without too much fuss. And I can either do that, or I can have a machine shop bore this out to accept the XJ hub assembly, which also fits the same as the Eagle. It just has a little bigger hub bore. But if you look, what I want to do is I want to maintain a nice down angle on my lower control arm. That means I can get a pretty good travel with a good camber curve throughout my suspension travel. And so the plan was to take this knuckle, flip the lower ball joint, so I have a nice distance from my lower ball joint to my wheel mount surface and upper mount ball joints. And so here's what I came up with. This is the line drawing of what I've come up with here. This is with the stock lower control arm. I take that back. This is a line going from where the ball joints will need to be to the stock inner control arm pivot. You see I got a slight down angle here. Here's my upper control arm with a slight up angle. And I should highlight that there so it's easier to see. And then if you see here, that's where my control arm lines intersect. Now it's quite a ways over here. You'd expect for a what they call, I guess it's a track with front view swing arm length. You'd expect it to be about here, but because it's an unequal length or a short long arm suspension, the upper control arm goes through an arc faster than the lower control arm when you go through bump. So this does get about 3 degrees of camber gain at about 3 inches of bump, which from what I've researched online is on track with stuff like Miatas and S2000s and really good handling sports cars. So you can see that there. You can see where I've drawn my steering alignment line, floating it a bit above the tie rod boss there, and that's my inner tie rod point. You can see my hub assembly. If I hide the knuckle, this is a representation of the hub assembly that I've just measured this manually off of the car and located it on the scan. But the main thing here is that I've come to a solution which is affordable, number one, pretty easy to perform, number two, and number three is it has good camber gain. It's got good scrub radius. It's got good kingpin inclination. It's got good caster. All the specs are right where I want them. Even the anti-dive geometry is pretty good. And you can see here, this is a representation of an inner pivot, upper control arm, inner pivot cross shaft. Reason I've got that, this is a 7.5 inch control arm. Now this is listed on Speedway as Speedway strut type upper control arm, aluminum cross shaft, 7.5 inch. But the important piece here is we've got an off-the-shelf control arm that will fit my application really well, really easy. It's got a ball joint bolt pattern here which nearly matches my planned ball joint. I'll just have to move these holes. Easy. This is a steel welded construction, which means I can weld onto this to mount my coilover, because that's the other thing here is with this plan, let's see, this is a more detailed mock-up here. With this plan, I'm able to run a fairly typical off-the-shelf coilover off the upper control arm that has good motion ratio, good spring inclination and decent travel. I'm sitting at about, I think, 12.6 inches between eyelets at ride height. So that puts me in the range of like 4-inch travel coilovers. So I'll have, I think, probably like 3 to 4 inches of bump travel, and a little less than that on droop travel. So I'm looking at coilovers either from like Ride Tech or QA1, something like that, right there. So so this is all very cool, but the cool part, the coolest part right now, I would say, is that now I think I'm going to execute this plan and give it a go. So what I've done, I've decided on my ball joint. My upper ball joint is going to be the S10 lower ball joint. And the reason I'm doing that is the S10 lower ball joint is the lower ball, or the loaded ball joint in the S10 system. So moving it to the upper ball joint along with the coilover means that the ball joint is still loaded in compression in the same manner. I know it's and more importantly, I know it's a strong ball joint. I know it's widely available. So I'm not changing how the ball joint is loaded. For the lower ball joint, the plan is to run a Chrysler K772 style ball joint, just because they're widely available and they're commonly used in aftermarket suspension systems, and they're easy to, and thus they're easy to fabricate with. I can buy off-the-shelf sleeves and mount points and stuff for them. So here is the coolest part, in my opinion, and that is that I'm able to take my 3D scanned lower control arm and in the virtual world create this part here, which locates my virtual ball joint in relation to the virtual lower control arm, which then leads me to this part here. And what this part is a bracket which I can 3D print. And in fact, I already have. And I can tell you right now, it bolts on, it fits. So I was able to model the thread for the ball joint here, model the threads for all the screws, and then when I printed this, I chased all the threads for the screws using a tap. The ball joint actually threaded in okay, just off the printer directly. And so this is really gratifying here. I was able to 3D scan this, confirm measurements experimentally. I was able to measure a dimension vertically or virtually and compare it to a real world measurement, print a part, and bolt it on, and it fits. So I've already got now the lower control arm with its ball joint in place. So what I need now is a ball joint reamer and the upper control arm. And then I'm basically ready to start assembling this front suspension. Anyways, I'll take you out to the garage now. So back out here, this is where I'm at now. I've 3D printed this control arm extension piece to mount this Chrysler K772 style ball joint. This is, if you want to look up the fitment, it'd be like, put in like 69 Dodge Charger or something, upper ball joint. But this is commonly found on McPherson or Mustang 2 retrofit suspensions and like just various aftermarket stuff. It's used in circle track. So these ball joints are going to be made for the foreseeable future. They're widely available. They're super common and they're nice and robust. It's a nice solid thread and ball joint. So this bracket securely locates this here to the point where I can actually move the stud around in the 3D printed bracket. This bracket actually turned out really well. It feels about as dense as like the fir wood, like 2x4 wood. Feels about as dense as that. I think I did 10% infill. This is a fairly large part. That sounded really funny there. This is a fairly large part to print. And if you have a printer and you're interested in printing stuff like this, I highly suggest you go check out Maker's Muse. And Angus from that channel did a great video on a settings for a 0.3 millimeter layer height fast build setting. And even on my cheap ass ANET A8, the print is acceptable. You know, it's the things are in the right spot. It's good enough for a bracket to begin fabrication. The only thing I did is I did model the threads for these screws here and these guys. These are 1/2 13, and then I did these in 5/16 18. 18? I think it's 18. Yeah, 5/16 18. And just because these holes are about 5/16. And then the threaded holes here I chased with a tap. The threads for the K772 are about, I believe the pitch is 12, and so 12 threads per inch. And I modeled it such that the diameter I measured with the calipers, the minor diameter of the thread on this, that's what I based it off of. So I used a regular 60-degree thread profile with that measured minor diameter, because the thread profile on this ball joint is really strange. It's kind of like the threads are like round. So I mainly am probably just picking up on the that inside part of the thread, and it's a slight interference fit. It threaded in nice. It's solid enough to do mock-up. Obviously, I'm not going to set the car on the suspension with this ball joint with this plastic bracket. So other than that, the new upper control arms they have a simple cross shaft, and so it'll just be a matter of locating two welded on bungs, little threaded bosses, onto the frame rail, at which point your upper control arm will go in there. And they're slotted too, so they'll provide me some caster adjustability in addition to what I already have with the track rod here. Outer tie rod, this fits nicely with the S10 knuckle down there. I may replace this knuckle in the future. This is the early style with these caliper ears like that. I may go to the later style one that has normal style caliper ears. That way I can adapt the brakes I want more easily. But I think tomorrow I will order those upper control arms, and because they're super cheap, they're like $40. I mean, how beautiful is that? A near bolt-on control arm for $40 because it's made for circle track stuff. So anyways, I'll order those, and the necessary ball joint reamer, which is a 7-degree taper. And the one I was looking at is the, was it? I think it was a Howe, but if there's two styles of ball joint reamers. You'll see there's like a helical cutting edge and a straight cutting edge, and I believe the helical cutting edge will work better with power drills or a drill press, depending on how I decide to do it, because I'm gonna actually have to remove quite a bit of material compared to, like, if I was just adjusting the fit. As for ball joints, once again, of course, forgive the mess. This is my S10 lower ball joint that I modified previously for mock-up, and I turned some of the taper off of it. But I've got this one here, and then I've got another spare S10 corner over there that I picked up. So I'll probably grab the ball joint after that, because it won't be all hacked up like this. But yeah, so the bolt pattern of this guy here, these two bolts appear to fit the exact same as the, what is it? I think it's 63 to 71 Chevy pickup C10 upper ball joint. which is what those NASCAR or circle track arms, that's what they have a bolt pattern on them for, is the Chevy C10 upper ball joint. And so what I'll have to do is just weld up the holes that go to these guys and re-drill them. So that'll be super easy. And then from there, I'll 3D print another bracket to aid in fabrication of the shock mount. I have just a terrible old, well, actually it's barely even old. It's just a terrible cheapo eBay shock that I'll use. This is actually, it's a full coilover thing here, but I'll use this cheap shock for mock-up and fabricate the upper mount for the coilover too. Or actually, I may do another 3D print on that. Speaking of which, on that coilover front, I've got my little bench lathe. So I think what I'll do is cut out a plate that has the 3-inch spring pocket in it. And so, you know, like where the original spring would have sat, I'll find a short length of pipe with the right inside, 3-inch inside diameter to fit on the little shoulder of the spring pocket. And then I'll have to step back up into the spring pocket in order to get the coil over where I want. It'll be a little bit of a trick, you know, that'll be a little bit of a fabrication project, but because all of that is going to be in kind of compression and tension, not a lot of shear, it's not going to be a super critical fabrication project. The other option I do have is that Ride Tech makes a coilover mount adapter for early Mustangs, and I suspect that will fit exactly on the AMC, because I think the upper spring perch is also 3-inch inside diameter on early Mustang, so it should fit the same. The only difference being that those shocks are designed to have not a lot of angle in relationship to the spring pocket. So the stud mount shock may, the bushings that they provide may not like it so much. So anyways, some questions to answer there, but generally suspension geometry wise, what we're looking at is S10 knuckle with an S10 lower ball joint as upper ball joint. So I maintain its compression loaded setting. Just remount that upper ball joint taper to accept the larger shank lower ball joint on upper position, and then re-ream the bottom ball joint boss to flip the lower ball joint and use that K772 ball joint, and that's it. Even the steering geometry works out to be just in about the right place. I may look into doing like a tie rod spacer to lift it up a bit. I think I'm going to test a bump steer just experimentally. Once I get it mocked up, I can cycle the suspension and measure bump steer. I don't think it'll be too bad. But anyway, I think that's a decision on front suspension and a plan to get the car low. The other thing worth mentioning, I did some experiments in the virtual world with CV axles. So I cycled the suspension virtually, and at 4 inches of bump, I believe, let me see if I remember correctly, I think it was around 20 degrees of angle on the outer CV when straight, and about 40 degrees at 4 inches of bump with 30 degrees of steering angle. So that, I think that's pretty good. I haven't experimentally confirmed the outer CV maximum angle, but what I see online is that somewhere between 40 to 50, or actually 50 to 60 is usually pretty normal. So if I can experimentally confirm that, that would be great. If I can go as high as 60 on the outer CV, I could even do as much as like 35 degrees of steering angle But I think even at 30, from the math I've done, the turning circle will be about 37 feet curb to curb, which is just 1 foot bigger than like a modern STI or something. So not crazy, you know, it should turn pretty well. The tighter I can make it turn, the better for autocross. Autocrosses oftentimes will have super tight elements that it's worthwhile having a really tight turning car. That's why like Miatas and stuff do so well, because they have short wheelbases. Miatas have crazy short wheelbases, by the way. It's like the shortest you can get. Anyway, so that's what we're looking at. S10 Knuckle, Eagle hub assembly, or possibly Jeep Dana 30 hub assembly, although I'd have to have the spindle machined for that. And then, you know, the upper and lower ball joints, a weld-in bracket on the bottom, simple weld-in bosses on the frame rail, a spring cup on the top, and or coilover conversion cup, and that's about it. So I think that's a wrap on suspension planning. Of course, the rear suspension will be a whole nother debacle, retrofitting independent rear. But I've got some ideas on that too, and I think it's pretty doable. So anyways, thanks for watching, and enjoy, and hope you enjoyed my ramble.